Swayam Prabha. Digital India. Educated India.
Okay, last class we were discussing the torsion equation which I wrote, because I will just give you a P double dot minus L omega square I m sine theta naught plus P cosine theta naught plus P minus L omega square I m theta psi cosine square minus plus MA. Okay. Suppose if we say phi is small, but theta naught is not small, that is the pitch angle, then you can approximate sine theta naught plus phi cosine theta naught, and then cosine as cosine theta naught minus phi. Okay, and this you have to substitute. You can collect the terms as phi, because otherwise in this form the equation is nonlinear. Okay, even the isolated torsion equation is a nonlinear equation. But your pitch angle which you set, that is theta 0, that can be large angle, that is the pilot input. But the phi is the elastic twist. That you say that is a small angle. So that is the assumption you are making here, and then you substitute back, then collect the terms of phi separately, and then leave out all the other terms. Okay. If you write that, that equation will be, maybe I will write here, that is you substitute and then rearrange all the terms, then you will have the equation will be L I m psi psi I m eta eta P double dot plus L omega I m psi psi minus I m eta eta cosine square theta naught minus sine square theta naught plus k p over L omega square minus I m theta psi 4 sine theta naught cosine P equals aerodynamic moment minus L omega square I m psi psi minus I m theta theta sine theta naught cosine theta naught plus L omega square I m eta zeta cosine square theta naught minus sine square theta naught. Okay. You see now, this is my equation. It is the linear differential equation because there is a phi double dot and there is a phi. So this is like mx double dot plus some kx equals some external loading. But you look at the external loading, MA is the aerodynamic load. There is one constant term. Please understand, this constant term is there, which is a function of pitch angle. Okay. Now you see, when
you have ignored the phi square term when we multiply sine theta. Phi is already.
this one, yeah, that, see, always phi is small. Okay, you make that assumption so that the torsional deformation is small but pitch angle is large. Large means it can be any angle, 10 degrees, 15 degrees, 5 degrees, but phi is a small angle. So the idea is, this kind of tells you, even if you do not have any dynamics, you keep the blade at a pitch angle, theta naught, and you rotate the blade. No aerodynamics, in vacuum. Okay. This is a constant term, which is a function of theta naught. If theta naught is 0, this term is what? This is 0, only this will be there. Okay. This is a cross product. If it is a symmetric cross section, then that will also go off. But if it is a non-symmetric cross section, you will have some term. Okay. But usually you take it symmetric cross section of the aerofoil. Then you can always find what is the twist, elastic twist phi due to a pitch angle. And that will be, because this is usually a small number, this is, you can neglect it. Okay. And even this quantity is larger than this quantity. Okay. You will find without dynamics, in the sense without any external aerodynamic loads, there is no phi double dot, equilibrium torsional deformation of the blade will be, phi equilibrium equals this quantity divided by this quantity, and that depends on what is the torsional stiffness. Suppose if it's a hinge point, there is no spring, then you will find the answer will be, phi will be exactly equal to minus theta naught. That means the blade will always come flat. In the sense, if you keep the blade like this and rotate it, the blade will always come down. It will be flat. Okay. This is the, because that is a natural equilibrium position. If you keep, there is always a twisting movement, nose down, twisting movement because of inertial load. Now you see the assignment which I gave. When we rotate it at a higher RPM, okay, you can have an elastic twist of the blade due to control system stiffness plus maybe the blade elastic stiffness. There is a nose down. One can actually reverse calculate what should be the k phi, assuming that this must be my pitch angle. Okay, so usually what you set it, pilot may give a command. This is my pitch angle. But what the blade experiences is not the same. Just dynamics, no aerodynamics. Aerodynamics comes, that will also change the angle of attack. But here, because of the elastic twist, you will find a loss in the angle of the pitch angle. That is due to the k phi. K phi plays a major role. That is why in the industry they calculate what is the control system stiffness. You will have swat plate, and then there is a hydraulic jack at the below the swat plate, above the control rods. You calculate the stiffness of the entire unit. You do a FEM model or some approximate calculation, anything but come up with the stiffness. Usually, of course, control rods are very small, so they are by EA over L. Okay, but the swat plate will have its own stiffness. That nothing is rigid. Okay, so that will give this. There will be a loss in pitch angle. Okay. And now I will not write any expression for MA, because this is basically aerodynamic load. You can use quasi-steady aerodynamic load or very simple instantaneous angle of attack, take it, put it. They are quasi-static. These are terminologies in the aeroelastic analysis. Okay. This is purely simple torsional dynamics of that. From here you can say, okay, if my Im theta zeta is 0, what is my frequency? Natural frequency of the blade in torsion. Like you have the flap frequency, you have the lag frequency, now you have the torsion frequency. If you take the torsion frequency, so omega r, that is basically, you have the stiffness term, you have the mass term, so you will have omega bar. That will be essentially this term divided by this term. Okay, so you will have Im eta eta cosine square minus plus k phi L omega square. Okay. And because L omega square, this you make it non-dimensional, so you will get another omega square will come, so the L omega square will go up. You have Im plus Im. This is nothing but the mass moment of inertia of the blade over a section. This is per unit section. Therefore, this is sum of this. This is the difference. Okay. Now you see when theta is 0, that is theta naught. When you set the pitch angle as 0, this term will, and usually this is much larger than, because you take thin aerofoil. Thin aerofoil, this quantity will be much smaller than Im psi by the inertia calculation. Therefore, you simplify this as, and theta naught is 0, you set. Then you will get a highly simplified expression. This is this and this 1 plus, I will put an approximation, k phi over Im L omega. Okay. This is my very simple form. That means this is, you can take it the blade torsional inertia. because I took this constant L into this will be torsional inertia of the blade about the quarter constant. And you have non-dimensional with respect to omega square. This is like a simple torsional spring. And this is due to inertia. 1 plus something. Like you had flap motion, where you always get 1 plus something. Here also this 1 will come. But this, if you have to be very careful how it comes. It comes because of this term. Okay, and sometimes people make mistakes. They derive the equation because these are all very small quantities. In a coupled torsion equation, it goes. But usually, control system has a sufficiently large stiffness because you don't want the control rod to be soft. Okay? Because whenever you give an input, it should faithfully go immediately, and there should not be any phase difference between this and that. So usually try to design that this is stiff, control rod stiffness. But if you take an actual blade, you have a control rod stiffness, you have the elastic GJ, twistness of the blade, both will contribute to that. Those equations are, you have to write the elastic blade. Here we assume the rigid blade. Where do you place the frequency of the torsion? See, like flap is around 1.09, 04, 03, like that. Lead lag is 0.25 or 0.7, the non-dimensional. Torsion, to keep it far away. Far away means usually it is around, but 3.5 is low torsional stiffness. So this is around 3.5 to 4.8, something like that. Around this range it will be. 4.5, 3.5 is very low. Torsionally soft blade. But you see this frequency is far away from flap and lag. Because you don't want to bring this and have a problem. This is mainly dominated to a large extent by control system. Okay. So if you want to analyze the blade dynamics, you need to know the control system stiffness. So that has to be calculated separately by stress analysis. Because you have to get some estimate of the torsion stiffness. Okay. And I will not go into the details because this particular term, when I wrote the tennis racket effect, that is basically this. See, even if Kφ is 0, that is 1. It's like a centrally hinged flap. So torsion also will have, if you disturb, it will oscillate like this as it goes around, once per revolution. That's all. Okay? It's like a plate. See, that is why when you analyze torsion, it is not a line. It is actually a 2D. About the axis, the blade can oscillate like this. Okay? And I think with this, we have kind of pretty much analyzed. This is, of course, this is the non-rotating torsion frequency because the spring inertia. That is all. This is non-rotating plus 1. That's what I wrote at the bottom. Okay. Omega non-rotating torsion plus 1 omega RT. Now this is all for isolated system. But if you ask what about the damping in torsion? Okay, lead lag we discussed. The damping is very small and usually external damper is provided. In torsion, the main damping comes because of aerodynamics. Usually it is about 10%. That's why there is no damper provided in torsion. Okay. Flap is heavily damped lead lag, you put an external damper, torsion is also damped out, isolated torsion. But for that you need to know unsteady aerodynamics, not the steady. Then only you will get the phi dot type of a term. Okay. You need to know the unsteady aerodynamics. How do you get the pitching moment? Okay. There are several theories, but that theory is in the aeroelasticity fixed wing theory. Okay. Fixed wing theory, is it applicable to rotary wing? But we use it. Okay. Applicability is something different, but that is the theory available and it is used, but with the correction for the inflow. That's all.
So fixed wing and rotary wing, other than the say axial force which is acting, so what would be this thing while calculating?
Torsion is pretty much there is no rotation. That's all. This is free. Fixed wing is only this. There is no rotation. This will not be there.
So but like modeling, say a rotating blade and a fixed blade.
Fixed blade is simple. Just a bending torsion problem. What you have learnt in structures 1 course. That's all.
So here we will be having axial term also.
Yeah, axial load. But I have made it as a rigid blade. Please understand, in all my assumptions, in all these things, I said my blade is rigid. Okay? But this question is, what will you have a centrifugal force? What do you do? There is an axial deformation will be there. Yes, it is there. But then you have to include the axial frequency. Okay, axial mode. Now, treatment of axial degree of freedom itself is several approaches. How it is done is, one is you make it as a rigid blade approximation. That's it. Why is it valid? The reason is axial stiffness is always much higher. It is EA than bending and torsional stiffness. Therefore, it's all right. Then in the bending problem, you have an axial, because it's a combined, if you want to treat axial motion, centrifugal force you have to bring it to effect. If you make it as a rigid blade, it is taken care of because you are not bothered about that. Only thing is, what is the effect of the centrifugal load? In flap motion you consider, lead lag motion you consider, torsional motion you consider. But if you say, no, I want to include elastic deformation in axial direction, then you write the axial equation. Then there are certain approximations made, which is usually what you normally make in a traditional bending problems. What do? You draw a line, reference line, and then it deforms. You see the length of that line does not change. Any material above that, this is what you learn. You take a cantilever beam, then you take a line, then you say what? This becomes. What is the length of this line? Is it the same or different or what?
Yes, you need to be.
Okay.
Yes, you need to be.
You make an assumption that
That it's same.
the reference, you call it neutral axis. Neutral axis does not extend. That is basically called inextensionality condition. If you impose that condition, then you can solve. So that is also done. Suppose you say, no, I don't want to do that also. Then you treat that problem. You include axial mode in your formulation. But it is really messy. It will complicate.
So in terms of aerodynamics, what is the difference in phi dot terms, say, between a static wing and a rotary wing? Aerodynamic force.
Aerodynamic, static wing and rotary wing, there are plenty of difference. First of all, the flow velocity is varying across the span. You will have a radial flow,
Yeah.
and you have a inflow. Everything is there. Flow is in all directions.
Okay, inflow can be accounted for, but how to,
What?
sort of,
What is your doubt? How do you take phi dot?
yes,
Is that
yes,
phi dot? If you because that is not taught you. Phi dot is, suppose you have to take a theory. This is the unsteady aerodynamic theory. You take an aerofoil. This is a quarter card. You take the half point, and you take some elastic axis. Okay, this is the most simplest model, and then mass center. So you take this. This point can come down and it can rotate. This is the elastic axis. So this is a 2D airfoil. Now the theory associated with the 2D is the Theodorsen's theory in the subsonic, incompressible. Okay, and that theory takes care of both the H and alpha. H is the heaving motion, alpha is the pitching motion. So you will get the lift and moment expressions are given about some n quarter card, and these expressions will be a function of alpha, alpha dot, alpha double dot, H, H dot, H double dot, H middle dot. Okay, so you will find everything. And this theory is by vortex model. This is unsteady aerodynamic theory. This is not taught. Suppose this is what I am telling you. Now if people want to get into aeroelastic problems of rotary wing, you start teaching this, or you teach, make all approximations and go and do it. That's it. You start with fixed wing aeroelasticity that. Okay. That is actually unsteady aerodynamic theory of a 2D aeroplane. Alright? Then you learn that. Then from there, how do you incorporate that in your rotary wing? And you can solve a rotary wing problem. This was the 1937 or something like that, Theodorsen's theory. But subsequently it was modified by Greenberg, then there is a Lois theory. But still Theodorsen's theory is, because it is experimentally proven to be valid for this. Now you can have, people start CFD, but CFD, how do you, because this gives the form of the equation which you can handle the stability of the problem. CFD is a numerical calculation. Okay, so it is the only time here you are analyzing in the frequency domain and get the stability directly. So there is a lot of difference. Nobody uses CFD for stability problem. Because then you have to do time domain integration and then try to predict the damping, etc. But still it may be a question. I have not seen any publication in that. They try to use for loads, but not for stability. Okay? These are differences because this is going more deeper into the modeling and then predicting what is happening. Okay? What we have shown here in the first level, I would call it the helicopter dynamics is the first level part. You learn isolated effect, you see what each blade does in flap motion, lead lag motion, torsion motion. And then you know the frequency you keep, what range they are. These are all isolated motion to understand what influences the frequency. Now, okay, you have learned up to this, next what? Okay, because that is a, where we build the subject. So I will see, after having analyzed the individual dynamics of the rotor blade, what are the various topics how people can go. Because isolated blade, okay, here you have flap, lag, torsion. Now, when you did this, what you have learnt is rigid blade. Rigid blade. Okay? This is the assumption you have made. Suppose you say, no, I don't want to make rigid blade. I want to treat it as an elastic blade. Then you have to go. That means modeling itself will lead to different direction. That is elastic blade. Okay. This, suppose I think one of you are giving that, how do you model an elastic blade? Okay. Whatever you learn, we will give. This by itself is separate study. Okay. Modeling an elastic blade, elastic rotor blade. Okay. With all complexities. Please understand. You will have, it's a twisted blade. It is flexible in bending, flap bending, lag bending, torsion, axial. So you will have axial, flap, lag, torsion problem. Complete all are there. One is structural model, then you have to have the inertia model. Then comes aerodynamics. Aerodynamics, I leave it as it is. Purely blade modeling is only structural and inertia. Okay? Okay. Structural and inertia. Only this. Actually, people spend their entire, some of the people, research career only on modeling structure. When you say blade modeling, you have to say what material. Isotopic material, composite material, how do you go, how do you model it, how do you get it, etc. This, people have spent their whole career on this. This is one direction. Another one, aerodynamic modeling is required if you want to solve the aeroelastic problem. Traditionally, I would put it traditionally, people use a relatively simplified aerodynamic model. Of course, simplified in the sense, quasi study with the dynamic stall, with some dynamic wake, etc. All, because that's what we have used. Now today CFD is entering into that. People have worked on that CFD problem, some of them, and they are trying to relate. But it's some approximation. Still, it is not fully advanced to the level that you can do everything. Okay. Now that is the aerodynamic model. So you can get into aerodynamic modeling. Okay. Purely. When I say aerodynamic modeling, what is that I do in the rotary wing specifically? I have to take care of the wake, which is the structure which the blade gives. You can have a lifting line theory. But here when you go steady, unsteady, you have to have both unsteady aerodynamic model. Okay. And then the wake, that is the inflow, which is generated at the rotor disc. We always use constant inflow and some uniform, but in hover only we add the variable. Forward flight is only constant inflow. Now is the inflow constant? It can vary with time. Then how do you model that? So inflow modeling itself has gone through very interesting, I would say, development. Very, very interesting development. And today that we have certain models which were developed. That is a dynamic inflow, dynamic wake, etc. These are all global theories. Still I am telling you, it's not a CFD per se. But still it is able to give you the variation of inflow when there is a variation in the rotor blade loading. The whole concept started like that. If there is a change in load, inflow will change. When the inflow changes, load changes. How do you relate these two? Okay. This is one line of problems. People have developed, spent time on modeling that. Another one is unsteady aerodynamic model for getting lift, drag, moment, etc. One is, please note, one is getting only the inflow. Another one is getting lift, drag, moment on sectional. So if you want to include stall models. Develop stall models, 2D, and then use it in 3D. Okay. So one can get into this also. But when you talk about aeroelastic, you need to have all. So you make trade-offs. The people who study aeroelasticity, they make a trade-off of this. And then they have a good model in everything and then use it for aeroelastic problems. So you can get into rotary wing aeroelasticity. Okay, this is one line. When I talk about rotary wing aeroelasticity, I have flap lag torsion. Okay. Initial development, if you see, that was not done with elastic blade. Rigid blade, but put flap lag, combined. Then put flap torsion. So flap lag problem, flap torsion problem, okay? Flap lag, then flap torsion, okay? These two problems were treated initially. That is one line, because people wanted to understand when the blade will go unstable, etc. Subsequently, because this particular problem, flap torsion looks like bending torsion problem of a fixed wing. Only thing is it is a rotary wing. The aeroelastic problem is bending torsion for fixed wing. Here it is flap torsion. Subsequently, they said that I think we should have everything, so flap lag torsion problems. Okay? But these results were generated with various couplings, various things. And I'll show one diagram, not actually one experimental setup, because it was essentially, see, this was a model rotor. Okay? So they put, because the model was built to represent the theoretical assumption. Please understand, that is it's the other way around. Not that they made a experimental setup and then you start modeling. It is actually whatever theoretical assumption you make, you incorporate in the experimental thing. So what they did was they put it is actually a nice kind of combination of flap and lag flexion at the same location. Okay? Because you always say spring model, and the spring model was put in, and there is no torsion. Blade was relatively stiff. This is almost like a rigid blade. But then they have pitch lag coupling. They also introduced pitch flap coupling, everything in this model. And just study only the stability of it. Okay. And of course, ground resonance problem also went on later. That I will come to that. So this is analyzing aeroelastic. Sometimes you may require stall. Please understand, because stall may be required in this stall modeling. Then stall modeling you have to bring in, even here, because your aerodynamics may not be good. So it is like a validating structural model was kept to the minimum. Check all the couplings, effect of aerodynamic modeling. Okay, that was this. But this is isolated blade. You are only solving blade problem. But in a helicopter, it is a rotor. That means I have to go for coupled rotor, fuselage, dynamics. that means fuselage is shaking, blade is moving, you have to study this problem. This is the actual problem. But in this, you have aeroelastic stability and response here. I will call it here aeroelastic stability and response. Okay. Only these two. Yes.
How do they measure this flap motion in this experiment?
Experimental measurement of flap motion means what exactly you were asking?
Flap response.
Okay.
If it
In flight test, they usually have some strain gauges in the root of the blade. Okay. So that will give you what is the bending moment. Flap bending moment, lead lag bending moment, and maybe torsional moment. Torsional moment normally goes to the pitch link load. So pitch link load, they measure what is the load on the pitch link. So flap is they put a strain gauge where they will measure the root bending moment. Please understand, it's not that the entire motion, every section they will do. Okay. But recently means maybe over 10 years, one UH-60 helicopter, that is the US Army, a experimental program was conducted on which they had some 220 ports, so many accelerometers, I don't remember, I have a figure, on the blade, both cardwise, spanwise, pressure ports, accelerometers. And they measured the in-flight load. That is only one test. And that is what people have been using it for predicting their models. Okay. Even yesterday there was a seminar, of course it was a Skype seminar. And they are doing it, University of America, because that data they are not supplying to everybody. It's a flight test data. And they did it for certain maneuvers. And then they are trying to predict what theory, how good is the experimental. Even now that research papers keep appearing. Okay. Because that has brought certain problems. Before that, the response was not properly predicted. Those things were identified. Now, see, with our model, we explain certain phenomena with our model, even though we don't have that data. If you change your aerodynamic model from simple to a more sophisticated, so we have 5 different models. So we said if you use the most simplest model, what will be the response? As you complicate the model, how the response really changes. Because there was some phase shift. Phase shift was where the minimum some load happens on an advancing side, something like that. They found out a experimental measurement and the theoretical was actually showing somewhere else. So they wanted to know what is really happening. That means I still have not understood. But those problems have been now solved. Okay, this is only the way. Otherwise, there is something called a tracking and balancing. Tracking means you want to track the tip path because all the blades must do same motion. Because if all of them are identical, right? No two blades are identical. There is always some difference. Okay. And they have a criteria by which they will bring the mass and the first moment within some limit. After that they put the blade, they rotate it, they have color code. Earlier they put some chalk and then they bring a cloth. They will know where it hits, each color chalk. Then they will know, oh, this blade is high, that blade is low, then they change it. Another way is they also have a vibration measurement, some insight. Because if blades are not tracking same position, you will have a 1 per rev vibration. They will try to minimize that. Okay, and that is the way. Otherwise, you can put some other wireless system and then measure. These are all measurement systems. What industry does, They will take, and then earlier only, what is that slip ring. Data will come through slip ring. Now you can have wireless also, but that you can have, but then technology has to be implemented on a real life thing and then take the data. Okay, that's what I think. If you want to add anything, you can add.
That's it. We are using Chadwick.
That is a vibration measurement.
Yes.
It will tell you which blade to adjust. That's all. So,
one more note, sir. The blade hinge moment versus the EA, the blade stiffness. Blade stiffness would be far higher than the hinge moment which we are taking at the.
no, blade
the
stiffness
elastomer.
means what? Blade stiffness is EI.
Yes, EI, sorry.
EI in flap. Yeah, but EI is a variable. It's not a uniform. See, the aerodynamic section to almost near the tip, it's a constant value. When you come near the root, the value will change. So it is essentially a variable property beam. Okay, it's not the same value through. It's not a uniform beam. It's a non-uniform beam with property varying near the root section drastically. It will come down in the middle. Really, they change very large over a small range.
So the spring which we are modeling for flat,
Uh-huh.
the spring constant would be far lower than the.
No. Spring constant is you try to estimate
Yeah,
the spring constant. Estimate. Please understand. Estimate the spring constant from frequency.
Yes.
That's all. And the hinge offset. Okay. That
So
is
if
all.
I measure that spring constant with respect to say
What
blades-
is the question of measurement of spring constant? There is no measurement.
Okay, sir.
You measure only the frequency.
Yeah.
From the frequency, because you know that suppose you take flap. Flap is 1 plus what? MXCG T over IB, right? Plus K beta over, right? This is omega rotating flap square. Suppose if you say non-rotating blade frequency, you can call it omega NR flap. That is only this quantity. This you can estimate, because in a hingeless blade it is very difficult to know where exactly is that. There is no one point. So it is like from the frequency you try to estimate what is this and what is E. Okay, if you assume this, you can get this. Equation is only one. Suppose if you have non-rotating frequency, then you can say, okay, this is my Kp. And then once I know that, then I can go and get it. There is another way. Or else they will say, if my K beta is 0, what is my hinge offset? Okay? That means that will be an equivalent articulated blade with what is the hinge offset.
So, but my question was, say, this KB water we are estimating, would it be of orders less than say EI, the blade stiffness?
No,
Because-
dimension wise they are different.
Yes.
Dimension wise, this is Newton meter per radian. That is what? EI is what? Newton meter square. What is the connection? No, connection is you can see one is a different unit, that is a different unit. You can't directly put it there. Of course, that affects this. You are looking at numerical value.
No, no.
Ah.
not the numerical one.
Then?
Say, my question was, say, is the hinge going to take the most of the bending which is going to happen, or the blade is going to bend a bit? So that would depend on
Not
the
blade, hinge. Blade, see, please understand, not that, okay, your question, blade also will bend,
Yes.
but it is in a second mode, third mode. Okay, first mode, majority of the deformation, if you say this is the hub, majority of the deformation will happen like this. This is the first mode. Usually you will find this is the, if it is a hingeless blade. But you can also get something here. There is nothing wrong. But it's a hingeless blade. If it is an articulated blade, then you have to calculate because the root hinge movement is 0. Okay, then the blade may have some other point the bending moment will be higher, but that is usually not very. You have to make a measurement. You put a strain gauge there and make a measurement only for, because that test I told you, they measured at 50%, 55%, something like that. Bending moment at 50%, and then try to correlate how your theoretical value matches with the flight test. But number wise, I don't see your question really. Is it a numerical value you are saying?
Not a numerical one.
Then
But if say the blade stiffness is say
EI, blade stiffness is EI.
yes,
See, these are all equivalent model. Equivalent model, that is all. If you actual analysis, if you want to do aeroelastic loads, you directly put the EI. You don't go to this model. See, this model gives an idea of what is my flap frequency, what is my hinge offset, that's all. Now this K beta, you adjust it to match that. If you want to represent your blade as a rigid blade with a root spring, then you go and then put this. That means what you are doing, elastic blade, you are representing by a rigid blade with a root spring. So the modeling, if you want, you can use this. And then you estimate the value, beta and E. So that estimation is easy.
but in this case the root is going to bear the brunt of the load.
Always, everywhere, the root only takes. Only the root.
Otherwise the blade
See,
would
if you really, otherwise, no, blade, middle point and all, no. Root only has all the loads. See, one is the centrifugal load. Centrifugal load is of the order of 100,000 Newton. Okay, phenomenally large. But the flap load will not be large. See, if you take flap shear load, if it is a 4,000 kg helicopter, it is 40,000 Newton for 4 blades. That means per blade it is 10,000. To support the weight of the helicopter by 4 blades. 4 shear load 10,000, but centrifugal load is around 100,000. But that does not mean flap load is useless, because that will give you the fatigue, because it will oscillate, all the vibratory load comes here, that is where the flap, okay, because it is a bending problem. Load wise, maybe magnitude may not be very large, but this cyclic load, vibratory part is the one which is the critical. Mean value and then vibration. Okay, mean is usually not tremendously large, because you take what? 4,000 kg helicopter means 10,000 Newton for 4 blades. That's it. That is the mean value in the shear. Okay. Is it clear? Okay, now I will go back to this, because I am giving only the type of problems. Okay. This requires now fuselage motion. So you will have fuselage motion. Okay. In addition to flap lag torsion. That means hub is going to move. This problem is more complicated. But all flight dynamics problems come under this, because you want to maneuver, you want to do something. Then you need to have a model for that. In addition, there are certain problems where you face instability. That is, I will just list them out. One is lag and fuselage. I will put it only lag fuselage. You will have ground and air resonance. Ground, air, resonance. Okay. And then flap, this is a gross approximation, flap and fuselage. This is flight dynamics. Okay. Usually that is what is done. But if you want vibration, then you have to have flap, lag, torsion, axial, everything. You can put axial also, and then fuselage. This is vibration. Okay. Now you see there are different types of problems. Okay, if you want to, you can say the most sophisticated analysis is coupled flap, lag, torsion, axial, fuselage motion, and fuselage also elastic modes of the fuselage. That is the most, but it is not practical. Okay, because it becomes, it's really, today it is not done. It's highly complex. And then if you want to take transmission, tail rotor, rotor fuselage, aerodynamic interaction, that's it. The problem is really very, very complicated. But how then the industry really designs go ahead and make a helicopter? You have to make simplifications. The simplification, ground resonance, when they analyze, they take only lead lag motion of the blade and the fuselage as a rigid body. You understand? And then solve this problem, ground resonance problem. So that means the modeling has now changed. Only I take lag and fuselage motion. Suppose you say I want flight dynamics. Okay. Flap motion and fuselage motion. Okay. Because the flap controls your loads, hub loads, your maneuver, everything. So you include. Plus there is also one more. What is the frequency range you are interested in? Usually the rigid body dynamics, the frequency is low. In the sense it is less than 1, 2, or maybe at the most 3 hertz, not hertz. Whereas this will be about 3, 5 hertz, 5 hertz. Okay. This problem you will have some 20 hertz, 40 hertz, everything. All the frequency will be there. Now you see, depending on the frequency range of interest, your modeling also changes. But technically, if you have a complete model, you can solve all the problems. Okay? But then, when you solve a problem, what approach you will use? So the mathematical technique becomes very important. If you want to analyze stability, then you have to know how do I analyze stability of a problem, of the system. If I want response, control response, how do I solve the control response problem? Okay. Now these are now going much deeper into the helicopter problems. So depending on the problem, you address that issue. So you find the modeling will change. Which of these I am going to address? See, these are, to a large extent, these are all the research problems. Even the flap is okay, but if you want to add all of them and then vibration and then flight dynamics and control characteristics, everything. Today models are getting developed. Everywhere people are improving their fundamental understanding based on some flight test or experimental data. Improve, keep improving. But to have a simple understanding, let us take just flap lag aeroelastic stability. That means you are having two motions of the blade. It's an isolated blade. If you want to go to rotor, now please understand, this is one blade analysis. This, you have to take all the blades. and all the blades, they are all kept at different azimuth locations. You have to take everything into account. Okay. And there are certain techniques associated with treating this problem. How do you treat? We have developed the equation for one blade, but I am putting 4 blades or 3 blades, 2, anything. As the number of blades, you have to have so many equations. Then you have fuselage motion. Then there is something like, hey, let me not look at individual blade. I will start looking at this as a rotor disc. I don't worry about the individual blade. I'll see how the disc is moving. Okay. Now again, in the flap motion, how the disc will move. In the lead lag motion, similar thing. That is where from a rotating frame to a non-rotating frame, some transformations one need to make if you want to analyze certain stability problems. Okay. Otherwise it becomes a little messier, complicated. But they do some approximations. Okay. We all said that the flap motion is like this. If it is coning, forward tilt, it is like, suppose if this itself is oscillating. That means there is an equilibrium position of the flap. About that it is oscillating. So now you see, hey, my flap motion itself is not a fixed value. It is going to be, if I say beta k, which is a function of time, I am going to write it, actually not even approximation, I will put it equal to, I will say there is a beta k equilibrium which can be a function of time plus this can also be, please note that this can also be a function of time, this can also be a function of time. This is a perturbation. Okay. But what is this? Looks like so this is the first thing you start learning, perturbation analysis, when you are analyzing either rotor fuselage stability or rotary wing aeroelastic stability. You have to know perturbation analysis. So what is the perturbation analysis? You have developed your flap lag equations. Assuming you know that inertial load, aerodynamic load and root spring model. You have developed a coupled flap lag equations. But those equations will be nonlinear. Okay. Then how do you solve stability, equilibrium? What you do is you take those equations. Those equations may have time dependent coefficients, everything. It's a nonlinear, complete messy equation. If it is a rigid blade approximation, those equations are ordinary differential equations. Okay, a rigid blade, ODE. It will be ODE. Of course, nonlinear, time varying, everything you can add all the. I'll tell you one way. If it is an elastic blade, this is PD. Okay. There will be partial differential equations. Elastic blade. Now, what are the various other additional characteristics? If you say, I am just giving you only the description. This ODE will be nonlinear, time varying coefficients. Okay. This also nonlinear, time varying. Okay, so you have everything, because unless you look at the equation, you will not know what I am talking about. In the sense, the coefficients of, you all know that they're very simple. In the ODE, we know that these are the plus kx f of t, right? But you know these are time varying. That means they are also functions of time, right? In hover, only the time varying is gone, but in forward flight, time varying will appear. Follow? So, if you solve non-time varying simple case, it's always hover problem. In the earlier days, people addressed hover case. But then, if a time varying system comes, how do I analyze stability? Okay. Even a simple case. How do I solve stability problem in a time varying systems? So that part I will cover in the last week. That is not really helicopter per se, but that is not usually taught in any other course. Time varying systems, stability problem. Okay. We will develop from systematic things. That will take about 2 lectures. You will learn that that is something which is totally different from what you learn from any of the courses. Okay. Now PDE, ODE. How do you solve which one? If you are taking elastic blade, that means you have to have a very systematic approach for addressing response stability problems. Okay. The PDE problems are converted into ODE. Unless you have studied vibration, vibration means not spring mass. It is the theory of vibration or continuous system vibration. You will not know how do I convert this to this. Okay. That is you have to learn the subject separately. On the other hand, you say, hey, I am starting directly rigid blade, that rigid blade I assume, then I will get directly the ODE equation. Straight away I go to ODE. Now, in the ODE, how do I solve? So the first thing is all the degrees of freedom. The degree of freedom is flap, degree of freedom is lag, if you are solving flap lag problem. Each degree of freedom, there is an equilibrium, there is a perturbation. Okay. So you always say flap, equilibrium, perturbation. And in the lag, equilibrium and perturbation. Okay. This is for isolated blade I am writing. So isolated blade means that K is only a dummy index, it need not be even there. Because there is no 1 or 2, 3 blade, you are looking at only one blade. Okay, so the K doesn't come into picture. On the other hand, if you go to this, you will have K index has to be there. Then how do you treat that class of problems? How do you treat this class of problems? So isolated blade, the index K has no meaning. Only one blade. Then what you do is you have your equation of motion, that is the nonlinear ODE. It is time varying. You substitute this in the equation. And then the product of perturbation neglected. That is, if you have a term like this, beta, zeta, which normally is there, you write it as beta k, okay, plus okay, I'll put and then plus zeta k T delta beta K. Okay, the product of this perturbation, you throw it out. You say it's a higher order term, I don't consider it. Then you collect all the terms which do not have the perturbation quantities. Write that separately. And all the terms which contain the perturbation quantities separately. Set both of them equal to independently to 0. Okay. Then you will get with two set of equations. So what you started with one set of equation, which is the flap-like, nonlinear, everything, you now have two sets of equations. One set of equation is the equilibrium, that is the term which contains this, that is called equilibrium equation. Okay? And these are perturbation. Okay? You will have like this. You first solve the equilibrium equation to get beta and zeta. First solve this. This can be a differential equation, but you have to solve it. Once you solve that, then you take that time varying and put it here. Then you solve the perturbation equation for stability. Okay? This is how the helicopter problems are solved. Okay? Stability is analyzed in the perturbation, equilibrium is analyzed in the actual nonlinear system. And I think with this I will close, because you cannot solve any one problem directly, because if I go into the flap-like stability, I have to give the full equation. I give the full equations, then you do it. The nature of equations, please understand, the nature of the equation can be in this nonlinear, time varying, ODE coefficients. Stability, linear, time varying coefficients. Now if you take the case of hover, okay, hovering condition, then what will happen is the ODE will become nonlinear algebraic equations. Okay, that means this time will not come. So this will go up. So you will have a nonlinear algebraic equation, flap-like in hover. You solve that. Once you know what is the flap deflection, what is the lag deflection, you substitute here, you will have a linear stability equation with constant coefficients, and you solve for eigenvalues. Eigenvalues, because you know the matrix algebra, solve for the eigenvalues, and you will get the stability results. Okay, this is the general procedure, and this is consistently followed. Whether you do numerically all this calculation or by hand, this is the procedure. But if it becomes time varying coefficients, how do you solve the stability? Okay, that part will. Well, there is one approximation where you convert this time varying into another frame. That is called the multi-plate coordinate. But that is not an exact transformation, but it is approximate. Convert the time varying coefficient to constant coefficient. Then you analyze. Another one is you apply Floquet-Lyapunov theory. Okay, that part I will teach in the last week. Okay, I think I leave you. If you have any questions, you can ask here. Because with this, pretty much your course material is and stuff.